Hello everyone, welcome to the P1 program. This lecture is called P104.2. Okay, in the first lecture of 104, we have discussed vectors and coordinate systems, scalars, vectors, and coordinate systems. In this lecture, which is a continuation of that first part, I'm going to um, finish off and explain a bit more on coordinate systems and what different kinds of coordinate systems. So before that, I need to introduce some simple stuff, right? So the first thing is that I have in the last lecture depicted that if you have two vectors p and k, those intercepts of p and k on x and y axes, when they are both added along with each other, you'll get that you'll add y component and x component of each of them together. That x's will be added here and this will be added here, and you get a new point in space, and that is going to be your resultant vector, right? So that's what I did last time. That's how I finished off. Now if you look at that case, you can see you can actually evaluate these vectors, the sum of two vectors, the effective resultant of such a vector p and k, in a different aspect, which is what you commonly study when you first encounter the addition of vectors and finding resultant of vectors. So that means if you have two vectors, you can either draw a parallelogram. Okay, a parallelogram of this is s and this is p. You can draw s and p here as well, and then draw a line in between, and you can say that's the resultant vector. Okay, that's one way. That's the same thing as here. Okay, we can draw a parallelogram here, right? And you can say the resultant. That's exactly what I did. But this is called the parallelogram law of vector addition. And there is another way. If you have two vectors like this, right, you can put one vector on this vector uh, in here, right, just like that, and you can draw a third side of the triangle, and you can say that's the resultant of the vector. It's all the same, right? If you draw parallelogram, or if you draw a rectangle or triangle, it's all the same. This is called the triangular law of vector addition, and this is called the parallelogram law. It is commonly used to find the direction of the resultant vector. Okay, so that's aside, and now I'm getting back to the coordinate system. So first of all, we have seen how coordinate systems works, that you can represent any vector in terms of x and y axis, right? Now you are representing a vector in terms of x and y. This is called the Cartesian system, and you can use a third dimension and introduce an c axis, and you can incorporate that into your system, and you can call it the three-dimensional Cartesian system. It's right there. Now what I have is another thing is called the polar coordinate system. So in polar coordinate system, instead of x y, you use r and theta. So you can use the radius and an angle to represent this same stuff, right? So for that, what would we do is that we do the same coordinate system, and we draw the vector, and we say that vector p has an intercept of px here and py here. Okay, and you say that you if you induce an angle theta in here, and the vector has a distance p, the length of the vector or the magnitude of the vector is p, then you can use trigonometry and find the this sides, the ratio of these sides. You can find sine of theta, right? Sine of theta, you can clearly see that py here will also be py, and px will also be px here. Okay, so these are parallel lines with the same vertices, so they are both equal. So sine theta will be opposite by hypotenuse, which is Py times magnitude of P. And also cos theta will similarly be adjacent by hypotenuse, which is Px by P, right? So you can say Px, which is the x-intercept, will be P sine theta, and Py will be Px will be P cos theta, and Py will be P cos theta, and Py will be P sine theta, right? So that's easy. Now you are using different a changing coordinate system. You have introduced a changing coordinate system where you have P x and Py in terms of P magnitude of P and theta. So this P is actually called the radius. If you want, you can consider that as the radius or the magnitude itself. So you generally represent P in terms of, or Px in terms of all the coordinate system of a vector in terms of some magnitude P and some theta angle. That's called polar coordinate system. Okay, this is called transformation. Okay, so with polar coordinate system, you can use it on a circular basis. Okay, you use polar coordinate system in a circular basis where you set some angle and you rotate that angle and you can see where it is. Okay, so if your particle is sitting here, you can just say that it is having a radius of r, and it is 120 or a fixed angle from the positive x-axis. With that, you can exactly pinpoint where the particle is or where exactly the position is. That's the use of polar coordinate system. Now coming to the cylindrical coordinate system. Okay, cylindrical. In this system, there is no much difference except that these polar coordinate system is used again and again. Okay, it becomes a continuously used loop of polar coordinates so that it becomes a cylinder. Okay, that's what it is. So the additional factor that is going to come in is that Px will be the same as we consumed for the assumed for the circle. It will be some radius times cos theta, and Py will be some radius or magnitude times sine theta. And now you have the additional advantage of changing the altitudes. Okay, you can go up or down. That means there is an additional axis which is called pz, which is just z. Okay, so that's the difference between polar coordinates and cylindrical coordinate system. Now a key aspect of both these system is that if you take say let's calculate what P is. Okay, so if you take x or x component, which is x which is equal to some r times cos theta, and y component is r times sine theta. Now if you can calculate r easily. You just all you have to do is just take the square of both and then sum it, right? So you get x square plus y square on both sides, which is equal to r square times cos square theta plus sine square theta. So you can say that so cos square theta plus sine square theta is a trigonometric identity which is equal to 1. So r square is obtained from that. So you can say r is equal to square root of x square plus y square. And also if you look at the graph itself, you can see that sine theta is that. Now tan theta will be equal to p of opposite by adjacent. So it will be p of y by p of x, or simply saying it will be y intercept by x intercept. So you can find theta, right, as in the case you can find theta as equal to tan inverse y by x. So you can use that these basics for both the system, for polar as well as the cylindrical coordinate system. They are both identical except that there is an z axis. Okay, there is an z axis. You can go in a cylinder. It's different from a circle because it has a height, right? That's the only difference. It's a three-dimensional aspect, whereas the cylinder, whereas the circle is just two-dimensional. Okay, coming to spherical coordinates or three-dimensional. Let's look at three-dimensional Cartesian coordinate system in a bit deeper level. Okay, this okay. There is one more thing. One more thing is that you always have to choose a right-handed coordinate system. Okay, you have to choose a right-handed coordinate system because if you choose a left-handed coordinate system, which I'll explain how it works, if you have x in this axis and y in this axis, then z must come here. Okay, if you reverse the x and y, then z must go down. Okay, so z must go down if it is opposite. You can easily understand that the need for this kind of a convention is to make sure that when you take certain operations like cross product, dot product, which I will explain later, in those things, if you are choosing a different coordinate system, then right-handed or left-handed coordinate system, when you alternate between them, the cross won't work. Okay, the cross product won't work, the direction will switch. So you have to follow the convention of a right-handed system. Now how can you easily understand if it's a right-handed system? Well, there is an easy way. You can stick your thumb and you can rotate your fingers of your right hand, and you can understand that from x-axis must be in this direction, and it must the fingers of your right hand must go to the y-axis. In that case, it's a right-handed coordinate system, and the thumb represents the z-axis. Okay, if it's a left-handed coordinate system, you can easily understand that the fingers will be curled around in the other direction. So x and y-axis, x will be here and x will be directed to y, and in that case z will be in this direction. So that's how you differentiate between the right-handed and left-handed coordinate system. This is the right-handed, and you must always use right-handed coordinate system. That is the only place where x cross y is equal to c. Okay, in the cross product, which I will explain, you don't need to worry about that. In this left-handed coordinate system, it is not the case. Okay, so always choose a right-handed coordinate system. That's one thing. Now if you are using this right-handed coordinate system, you can see that you have a vector like this is your vector, say p. Okay, so the angle made with the c axis, okay, this angle is called theta. Okay, that's first thing. And when you what you can do is that you can actually make an intercept. Okay, we did an intercept of x and y in the case of polar coordinates. Now similarly you can make an intercept of p in the xy plane itself, right? Xy plane itself, not the x axis or y axis, but in the xy plane. That this is the plane there. Okay, so in this xy plane you can make an intercept, and you can get an intercept which is looks like this. Okay, this is called p of xy. You can always make other intercepts in zy plane or zx plane as your convenience, but for here I am using the xy plane for the intercept. So this in this xy plane, this angle is called, okay, this angle, I hope you can see that, this angle is called phi. Okay, so that's the first angle theta and the second angle phi. Okay, that's the two angles. Now in the in the three-dimensional Cartesian system, you can now estimate. I'm going to redraw that. Okay, okay, This is the system. And when you make an intercept like this, right, this is our intercept here, this is our intercept, and this was actual vector was like this, and we made an intercept in the c-axis. Okay, so that intercept makes angle phi here, and this from the z-axis makes an angle theta, and this is the x-axis, this is the y-axis. It's a right-handed coordinate system. Now if you look at this triangle, right, this triangle, you can see this has the magnitude of p. If the vector p, it has a magnitude p, so this length will be the same as this length, right, this length will be the same as this length, right, it will be, so say px of y, right, that's the intercept right there. Those are parallel lines, so they must be the same, and this length is called pz. Okay, with that right there, now I'm going to say what is let's say this is the angle theta, so let's call what is p, let's let's find out sine theta, right, sine theta will be pxy by magnitude of p, right, magnitude of p. And similarly cos theta will be cos theta will be what, pz, pz by magnitude of p. Okay, so you got sine theta and cos theta here. Now you can say that uh, pz, right, pz will be, so you can say, you can easily say that pxy is equal to p times sine theta, sine theta, and pz is magnitude of p times cos theta. Okay, so we have found out pz, and we have found out what pxy will be, and now we need to find out px and py. Okay, okay, now if you look at the same graph, you can look at this from above. Okay, if I'm looking from this direction downwards, you will see that y-axis will be in this direction and x-axis will be in this direction, right, and this will be our p of xy, right, this will be p of xy, right, and this angle, as I said earlier, is called phi. Okay, so you can say that x intercept, this will be p of x, right, this will be p of x, sorry, the p of phi, and this will be p of phi again, it's the y intercept, and also this will be p of x, and this will be p of x as well. Okay, so now if you take the sine of phi, you get opposite, which is py by magnitude of p, which is pxy, right. Similarly, if you find cos phi, you get p of x by p of x by p of xy, right. So now you got py equals p of xy times sine phi, and p of x is equal to p of xy times cos phi. Okay, now you can substitute the value of p of xy here, so it's p sine theta, so you can write down it's p sine theta, sine theta times sine phi, and p p of y will be p sine theta times sine phi, and p of x will be p sine theta times cos phi. So we have found out in in spherical coordinates, in Cartesian three-dimensional spherical polar coordinates. This is called spherical polar coordinates because we are representing uh, this whole vector p in terms of theta, phi, and r, which is p. Okay, which is the magnitude of p is the radius, or the radial component. So we are representing in terms of that. So we have found out what py component will be, we have found out what px component will be, and we have found out what pz component will be. So pz will only be dependent on theta and radius, py will be dependent on radius, theta, and phi. Also px will be dependent on radius, radial vector, radial distance, theta, and phi. Okay, so that's how we resolve these situations. Now you can, maybe you can we can use it on a real case. Okay, maybe if I have say a vector, say a is equal to, okay, 3x cap minus 2y cap plus say 4z cap. This is going to be a bit complicated. Okay, anyway, we are going to use that. We just give the right-handed coordinate system, right? Right-handed coordinate system. And if you see this vector, right, this is minus y, this is minus z, and this is minus x, and this is plus x, and this is minus x. Okay, that's the right-handed coordinate system. Now if you see the x-intercept here is 3, right? So it will be 3 here, positive 3, and the y-intercept is minus y, so minus 2, so it will go here. Okay, and z is plus 4, so it will go here. So you can see, you can make a diagram like this, and you can go like this if you want. I want it to get right. Okay, that's how it looks like. Okay, I'm going to redraw it anyway. So the box will look like something like this. Okay, 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 that's how it look like as the same box. Now this is the point minus 2, this is the point of x, which is plus say plus 3, and you have z, which has an intercept in here, which is plus 4, and now you will have the vector which is directed in such a way like this. Okay, that's the vector right there. Now if you look closely, so this is the x-axis. If you look at the x-axis, this is the x-axis, this is the y-axis, this is minus x, this is plus y, and this is plus x, and this is plus c. If you look at this, you can find that the angle made with the y-axis is c-axis. Okay, I'm not going to use that. C-axis is this angle. This angle is called, okay, this is called theta, right? And the angle made with the x-axis will be x will be intercepted, right? So it will be intercepted like this, and the angle will be some angle from the positive axis to this direction. So if you look from above, if you again look from above, you see that this is the x and y axis. The intercept of xy will be looking like this, and the angle will go all the way around, right? All the way around, it will be greater than 180 from x-axis. So from x-axis it will be like that, and from y-axis it will be minus angle, right? It will be minus angle. So that's one thing. Now I can just, all I have to do is just substitute in the equation of solving polar coordinates. Now you can find out the magnitude of this vector, right? You can find out the magnitude of this vector, which is square root of 3 square plus 4 square plus 9 square plus 4 square plus 16, that is 29. We have already done that, right? So it will be 29, which is the magnitude of A. Okay, so A's magnitude we have found out. Now uh, now cos theta will be Az will be Az. You can look back at the equations if you want. It is Az times the magnitude of A. So Az component will be 4. So I'm going to look at the other thing, 4 by root of 29. Okay, I've done this already, so it will be around, theta will be around 42 degrees. Okay, 42 degrees. From now onwards you have to refer the earlier thing that we have done. Okay, I cannot always look back. So it's Ax will be A sine theta, sine theta cos phi, right? So it will be, that's Ax. We have found out theta, and also Ay will be A sine theta sine phi, right? Sine theta sine phi. Now you get phi. If you solve this, you get phi. I leave that to you. Okay, if you solve this, you get phi, which is equal to 326.3 degrees around. Okay, and you get a phi value of that, and you get a theta value, which we already got, which is 42 degrees. Okay, so we will get theta and phi. If you solve this equation, you can substitute the theta value here, and you know the A value, and you can find out the um, phi values. Okay, so with that I'm going to close this whole lecture, and I hope you understood what the basics of um, polar coordinates, cylindrical coordinates. I know it's a long one. Anyway, we have found out what we have discussed: polar coordinates, spherical polar coordinates, then cylindrical coordinates, and Cartesian system. So I hope that's all the systems that we are going to use in the forthcoming lectures. So thank you.